So hello everyone, in my last video lecture I had covered the topic Winograd convolution algorithm and I had discussed the steps that are involved in this algorithm. So now I am going to take an example and using these steps I will calculate the convolution of any two polynomials. So example. Okay, so given two polynomials HP, that is h0 plus h1p, and xp, that is h0 plus x1p, and their linear convolution is given by sp, that is equal to hp into xp. So this is a 2 cross 2 convolution. Two terms in hp and two terms in xp, 2 cross 2 convolution. So now we have to implement it using Winograd algorithm. So the problem is implement it using Winograd algorithm. And given is m of p, that is product of all the moduli, that is given by p minus 1 and p square plus 1. So mp is product of three different polynomials. So I can say that m0p is equal to p, m1 p is p minus 1, and m2p is p square plus 1. So you can notice that all are relatively prime. Okay, so this was the first step, determining the values of moduli, and it is already given, so we don't have to compute it. Okay, so in step 2 you have to compute capital M of I p, that is given by small m p and divided by m of I, small m of I p, for I equal to 0, 1 and 2, because this is factorized into three different factors. Okay, so for I equal to 0 we have capital M0p, that is m of p divided by m of 0p, and this will be m of 0p is p and p will be cancelled out, and the product of 2 will be p cube minus p square plus p minus 1. Okay, m of 1p, it is given by mp divided by m of 1p, and m of 1p is p minus 1, so p minus 1 will cancel out, so it is product of p into p square plus 1 whole, so that is p cube plus p. And at last m2p, that is given by m of p divided by m of 2p, and m of 2p is p square plus 1. So p square plus 1 will cancel out, and it is the product of p into bracket p minus 1, that is p square minus p. Ni of p for I equal to 0, 1 and 2. Using the identity Ni of p into capital Mi of p plus small ni of p dot small mi of p, that is equal to 1. 1 is GCD of capital MP and small mp, that is known, and that you have to solve using Euclidean GCD algorithm. Okay, so for I equal to 0, I have n0p dot m0p plus small n0p dot small m0p, that is equal to 1. Now this m0p is given by p, and capital M0 p, that we have calculated as p cube minus p square plus p minus 1. So we already know that GCD of these two numbers is 1. Okay, and at this point I am not going to discuss this in detail, Euclidean GCD algorithm. Okay, what is the main steps to evaluate NIP, that I will cover here. Okay, so you can study in detail that how these two numbers, if two numbers are given, so and if their GCDs are known, so this can be represented in this form. Okay, so now this value, that is capital MP, p cube minus p square plus p minus 1, that is m0p, it can be represented in a form p dot some quotient. If I divide this by p, I will have some quotient plus remainder. Okay, so this is m0p into some quotient part plus remainder. Okay, so this you have to do in a particular manner. Okay, so p cube minus p square plus p minus 1, dividing this by p, so this is p square, so this will be p cube. Okay, this is minus p square, so minus p square, this is p, so plus 1, and minus 1 is remainder. Okay, so I can write m0p, this p as, this is capital M0p and this is small m0p. The quotient is p square minus p plus 1, and the remainder is minus 1. Okay, so at this point you have to stop. This remainder is not a function of p, So at this point you have to stop. Okay, now consider this equation and this equation. Okay, so you have one small m0p, small m0p, capital M0p, capital M0p. So you can rearrange the equation, and by comparison you can evaluate capital N0p and small n0p. Okay, so rearranging the equation, I have 1 is equal to m0p multiplied by p square minus p plus 1, p square minus p plus 1, and taking capital M0p on the right hand side minus M0p. Okay, comparing this with equation 1 is equal to small m0p, small n0p plus capital M0p, capital N0p. So small n0p is p square minus p plus 1 and capital N0p is minus 1. Okay, so now for I equal to 1, I have small n1p, small m1p plus capital M1p and capital N1p is equal to 1, and M1p is p minus 1 and capital M1p is equal to p cube plus p. So I can represent capital M1p is equal to small m1p into quotient plus remainder. For that I have to divide capital MP, that is p cube plus p, with small m1p, that is p minus 1, so that this will be p square, this is p cube minus p square minus plus p square plus p, and now plus p, so it will be p square minus p, this will be 2p, and multiplying p minus 1 by 2, so I have 2p minus 2 and the remainder is 2. So capital M1p is small m1p, quotient is p square plus p plus 2 and remainder is 2. This remainder is not a function of p, so I have to stop at this point. Okay, now dividing both the side by 2, I have m1p divided by 2, small m1p divided by 2, p square plus p plus 2 plus 1. So now compare this equation and this equation. Okay, so just I have to rearrange this equation. So 1 on the right hand side and remaining terms on the left hand side. So m1p by 2 minus small m1p by 2 bracket p square plus p plus 2, that is equal to 1. So compare this to equation. So I can say that n1p is 1 by 2, capital N1p is 1 by 2 and small n1p is minus 1 by 2, p square plus p plus 2 minus 1 by 2, p square plus p plus 2. So for I equal to 2, we have to evaluate n to p, capital M to p plus small n to p, small m to p, that is equal to 1. And capital M to p is given by p square minus p, and small m to p is given by p square plus 1. Okay, so I will represent capital M to p as a product of small m to p multiplied by some quotient plus remainder. So for this I will divide p square minus p by p square plus 1. Okay, so for 1 I have p square plus 1 and the resulting minus p plus 1. Okay, so m of 2 p is m of 2 p, quotient is 1 and remainder is minus p plus 1. So this remainder is function of p. So now small m to p will be divided by this remainder, so we can express this in the form small m to p is equal to minus of p plus 1 multiplied by quotient plus remainder. So for this we have to divide small m to p, that is p square plus 1. So p square plus 1 will be divided by minus of p plus 1. So minus p, this is p square plus p, and minus we have minus p plus 1 and plus 1, so minus p minus 1, so remainder is 2. Okay, so small m to p is product of minus p plus 1, quotient is minus p plus 1 bracket plus remainder, that is 2. So this remainder is not function of p, so stop at this point. Dividing both the side by 2, I have m to p divided by 2 minus, taking this to left hand side, this will be plus p plus 1 bracket minus p plus 1 divided by 2, and this is equal to 1. Okay, now from this equation, so I can substitute the value of this p plus 1. Okay, so from this I can write p plus 1 as m to p dot 1 minus capital M to p. So substituting this value into this equation, I have to p by 2 as it is, p plus 1 as it is, and this is minus p plus 1, and instead of this p plus 1 I will substitute this. So this is m to p minus capital M to p. divided by 2, that is equal to 1. Okay, now this equation is almost similar to this equation. So now, properly arranging the terms and comparing with this equation, we can easily find out the value of capital N2P and small n2p. Okay, small n2p plus capital M2P, capital N2P, that is equal to 1. We can write small m2p is equal to 1 by 2 minus p plus 2, and small capital N2p is equal to 1 by 2 p minus 1. Okay, so now I am summarizing all the calculated value. So that I can use it easily for further calculations. So for I equal to 0, 1 and 2, I have calculated small mi p, capital mi p. Okay, small mi was already given, so I have calculated capital mi p, capital ni of p, and small ni of p. Okay, so the values are p minus 1, p square plus 1, p cube minus p square plus p1, p cube plus p square minus p minus 1, 1 by 2, 1 by 2 p minus 1, and p square minus p plus 1 minus 1 by 2, p square plus p plus 2, and minus 1 by 2 p minus 2. So step 2 is completed at this point. Now in step 3, we have to calculate h of ip, that is equal to h of p mod m of I p, and x of I p, that is equal to xp mod MIP for I equal to 0, 1 and 2. Okay, so h of 0p will be equal to HP is h0 plus h1p, and mod m0p is p. Okay, so m0p is p, and the value will be, okay, so put p equal to 0 in this polynomial, so the result will be the remainder, so that is h0. For h1p, you have to take h0 plus h1p mod of m1p, so m1p is p minus 1. Okay, so this is, so put p equal to 1 in this polynomial to calculate the remainder, okay, as discussed previously. So putting p equal to plus 1, we have h0 plus h1, and calculating h2p in a similar way, so h2 of p is h0 plus h1p mod m2p, that is p square plus 1, Okay, so at this point you can see that the degree of moduli is greater than this h0 plus h1p, so the remainder will be h0 plus h1p itself, h1p. Now calculating x of 0p, so that is x0 plus x1p plus x2p square mod p, and this is x is 0, putting p equal to 0 in this polynomial. So x is 0, x1 of p is equal to x0 plus x1p plus x2p square mod p minus 1. Put p equal to 1 in this polynomial, the answer will be x0 plus x1 plus x2, and x2p, that is x0 plus x1p plus x2p square mod p square plus 1. Okay, so you have to put p square equal to minus 1 in this polynomial. So the remainder will be x0 plus x1p, p square is minus 1, so minus x2, so that can be written as x0 minus x2 plus x1. Okay, so now we have to calculate s of ip, that is h of ip into x of ip for I equal to 0, 1 and 2. So s of 0p is h0 x0, and that can be written as s of 0 subscript and superscript 0, 0 for this and this 0 because the power of p is 0. S of 1p is h0 plus h1 into x0 plus x1 plus x2, and this can be written as s of 0, 1. Again, this is not a function of p, power of p is 0, so the subscript is 0 and superscript is 1 for this, and s of 2p is h0 plus h1p into x0 minus x2 plus x1p, and that can be written in the form h0 x0 minus x2 minus h1 x1 plus h0 x1 plus h1 x0 minus x2 bracket p. So this can be written as s of 0 2. It is not a function of p, so subscript is 0, this term, and this term can be written as, this is a function of p, so p is to power 1 and superscript is 2. This is s0 of 2 and s1 2. So you can notice that one multiplication is required to implement this, one multiplication is required to implement this, and 1 2 3 and 4 multiplication is required to implement this. So one multiplication for this, one multiplication for this, and 4 multiplication for this. Okay, so if I rewrite this equation, so if I rewrite s0 of 2, this equation as h0 x0 minus x0 plus x1 minus x2 minus h1 x1, in this form, and if I rewrite this equation s of 1 2 into the form x0 plus x1 minus x2 minus h1 minus h0 multiplied by x0 minus x2. Okay, so now if you notice at this point the number of multiplications are 1 multiplication 2, this is the same, and this is 3, so now 3 multiplications. So total number of multiplications required are 1 plus 1 plus 3, that is 5. Okay, so just by rewriting this equation in some other form, the number of multiplication is reduced. This equation can be represented in a matrix, so I can write S0 of 2, S1 of 2 the form of matrix. So this is 1 0 minus 1, 1 minus 1 0, this is h0 0 0 0, h1 minus h0 0 0 0 h0 plus h1, and at last x0 plus 1 minus x2, the second row x0 minus x2, and in third row that is x1. So number of times I have demonstrated that how you can write any particular equation in this matrix form, so I leave it as an exercise for you to break or decompose in this kind of form. Okay, so in step 4 you have to compute s of p, that is equal to summation I equal to 0 to 2 s of I p capital N of I p capital M of I p mod MP. So we have calculated all the required values, and this SP can be written as S0 plus S1P plus S2 P square plus S3P cube, and on the right hand side I have, substituting the values, I have minus S of 0P in bracket P cube minus P square plus P minus 1 plus S of 1P dot P cube plus P plus S of 2P divided by 2 P cube minus 2P square plus P mod P raised to power 4 minus P cube plus P square minus P, so multiplying all the three moduli. Okay, so I have S0 plus S1P plus S2P square plus S3P cube, that is equal to P raised to power 0 S of 0 0 plus P raised to power 1 bracket I have minus S of 0 0 plus S of 0 1 divided by 2 plus S02 divided by 2 plus S01 2 divided by 2. Okay, so just I am substituting the value. I am leaving as an exercise for you because this will be very lengthy if I put the values at very time consuming. So just it is a simple mathematical problem. Plus p square bracket s of 0 0 minus s of 0 2 plus p cube the bracket minus s of 0 0 plus s of 0 1 by 2 plus s of 0 2 divided by 2 minus s1 of 0 divided by 2, and this can be written in the matrix form as 0 s1 s2 s3, and on right hand side I have 1 0 0, that is post addition matrix. 1 0 minus 2 0 minus 1 1 minus 1, and this will be a column matrix with value s of 0 0, half s of 0 1, half s of 0 2, and minus plus half s of 1 2. So again I am leaving this as an exercise for you because I have already demonstrated multiple times how to break in this form. Okay, and I am again skipping some steps, and the final form will be substituting the values of s0 and all. The final form will be keep on decomposing. This will be the final form. So at this point you can notice that this is the addition matrix. So total number of additions are 1 2 3 4 5 6 7 8 9 10 11, and total number of multiplications we have already evaluated, that is 5. So using Winograd algorithm, for 2 cross 3 convolution, number of multiplications required are 5 and additions required are 11, whereas using direct form, multiplications required were 6 and additions required were